It came from deep space, silent, cold, and alone. And as it passed the Sun, 3I-ATLAS did something no comet ever has. It accelerated. But not because of gravity, not because of jets of gas or solar wind. It just pushed itself. NASA's new data confirms it. A force no one can see, no one can explain, pushing it against gravity itself. Avi Loeb predicted this exact moment, months before it happened. He says it could be a relic, a fragment of alien technology, a defunct probe, or even a light-powered sail drifting through space gliding through our solar system. Skeptics say impossible. But the numbers don't lie. Is this how first contact begins? Not with words, but with a subtle shift in velocity, a quiet hello written in math. Stay until the end, because what NASA just revealed might be the first real sign that we're not alone. If this mystery continues to have you on edge the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. Breaking news. What if we've just detected the first technological signature not from Earth, but in interstellar space? What if, right now, somewhere between Mars and Jupiter, a fragment of alien engineering is drifting through our solar system, and we almost missed it? This isn't science fiction. This isn't a conspiracy theory whispered in the dark corners of the internet. This is NASA data. This is orbital mechanics. This is happening right now, and the clock is ticking. On October 29th and 30th, 2025, an object designated 3I-ATLAS, the third confirmed interstellar visitor to our solar system, made its closest approach to the Sun. Scientists call this moment perihelion. For most comets, perihelion is predictable. You calculate the gravitational forces, you account for the solar wind, and you watch the object follow the laws of celestial mechanics, like a billiard ball rolling across the felt of space-time. But 3I-ATLAS didn't follow the script. Instead, it accelerated. Not a little, not within the margin of error. It accelerated in ways that gravity alone cannot explain. NASA's Jet Propulsion Laboratory, using data from the Punch satellite's Wide Field Imager 3 instrument, measured something extraordinary. The object experienced a radial acceleration of approximately 135 kilometers per day squared, pushing it away from the Sun. Simultaneously, it showed a transverse acceleration of about 60 kilometers per day squared, perpendicular to its trajectory. Those numbers might not mean much to you yet, but here's what they represent. A force acting on this object that has nothing to do with the Sun's gravity pulling it, or any planet nudging it along. Something else is pushing 3I-ATLAS, something we can't see. Harvard astrophysicist Avi Loeb predicted this months ago. Loeb, if you're not familiar with him, is the astronomer who suggested that Oumuamua, the first confirmed interstellar object discovered in 2017, might not be a rock at all, but rather a piece of alien technology, perhaps a light sail or a defunct probe tumbling through the cosmos. The scientific community didn't take kindly to that suggestion. They called it speculative. They called it attention-seeking. Some called it worse. But Loeb didn't back down. He said we should be open to extraordinary explanations when we encounter extraordinary data. And now, with 3I-ATLAS, the data is getting harder to ignore. The acceleration isn't the only anomaly. There's the brightness. 3I-ATLAS brightened rapidly as it approached the Sun, which isn't unusual for comets, except the rate at which it brightened is unusual. Studies tracking the object's photometry show a relationship between brightness and distance that follows an inverse power law with an exponent of -7.5. That's much steeper than typical comets, which usually brighten at rates closer to -2 to -4. What does that mean in plain language? It means 3I-ATLAS got bright fast, faster than our models predict for a chunk of ice and rock warming up under the Sun's heat. Then there's the colour. Comets are supposed to scatter light in a way that makes them appear reddish, or neutral in hue, because they're coated in dust and organic molecules that absorb blue wavelengths. But 3I-ATLAS appears unusually blue. Loeb called this very surprising. Blue light suggests either very fine dust particles or something reflective, something metallic, something that doesn't fit the profile of a dirty snowball wandering in from the cold. So here's the central question, the one that's going to haunt you for the next hour. Could 3I-ATLAS be a fragment of alien technology? Could it be a defunct probe, a piece of a light sail, or even an operational spacecraft performing a gravity assist maneuver around our sun? And if it is, if this is the moment we confirm that we are not alone, that intelligent civilizations have sent their machines into the galaxy, what happens next? This isn't just about one object. This is about what we assume visits our solar system, what we assume about the universe, and what we assume about our place in it. If 3I-ATLAS is artificial, then every comet, every asteroid, every piece of cosmic debris becomes suspect. We'll have to ask ourselves, how many times have we looked at something strange and explained it away because the alternative was too uncomfortable? How many visitors have we missed because we weren't ready to see them? In the next hour, you're going to see the data. You're going to hear the scientific arguments, the controversies, and the institutional responses. You're going to learn what happens next, what telescopes are watching, what observations are planned, and what those observations might reveal. But first we need to understand how solid this claim really is. We need to dig into the measurements, the instruments, the engineers who spotted the anomaly, and the scientists who are either defending it or tearing it apart. Because here's what you need to know right now. This isn't settled. The scientific community is divided. Some researchers are cautiously intrigued, others are vocally sceptical, and a few are quietly terrified, not because they think 3I-ATLAS is alien, but because if it is, we're not prepared for what comes next. We don't have protocols for this. We don't have contingency plans. We barely have the telescopes aimed in the right direction. Coming up next, we dig into how those numbers were measured, why some scientists are calling this the most dangerous comet encounter we've never talked about, and what it would take to prove once and for all that we're looking at something not made by nature, but by minds like ours, or perhaps very unlike ours, from somewhere out there in the dark. Part 2. Data and Source. Deep Dive. Time 0.5s. The measurements that changed everything came from NASA's Punch satellite, specifically an instrument called the Wide Field Imager 3. Punch stands for Polarimeter to Unify the Corona and Heliosphere, and it was designed to study the Sun's outer atmosphere and the solar wind. It wasn't built to hunt for alien technology. It was built to watch plasma and magnetic fields ripple outward from our star. But sometimes the most important discoveries come from instruments pointed in the right direction at the right time, even if they're looking for something else entirely. David Farnokia, a navigation engineer at NASA's Jet Propulsion Laboratory, analysed the images. Farnokia specialises in orbital mechanics, the mathematics of trajectories, the predictions of where objects will be based on gravity and momentum. He stacked images from Punch, tracking 3I-ATLAS frame by frame as it swung past the Sun. What he found didn't match the predictions. The object was accelerating in ways that pure gravity couldn't account for. The radial component, the acceleration directly away from the Sun, was approximately 135 kilometers per day squared. The transverse component, perpendicular to the Sun object line, was about 60 kilometers per day squared. Let's put those numbers in context. A kilometer per day squared might sound small, but over the course of a month, that acceleration compounds. Loeb estimates that over 30 days, the non-gravitational force would shift the object's trajectory by roughly 10 Earth radii. That's about 80,000 kilometers of drift. In orbital mechanics, that's enormous. That's the difference between a comet arriving where you expect it and a comet showing up in the wrong place entirely, forcing you to recalculate everything you thought you knew. The geometry of perihelion matters here. On October 29th and 30th, 2025, 3I-ATLAS reached its closest point to the Sun at approximately 1.36 astronomical units. That's about 203 million kilometers. For reference, Earth orbits at 1 astronomical unit, so 3I-ATLAS passed the Sun at a distance slightly greater than Earth's orbit. Not close enough to vaporize, but close enough for solar heating to matter, close enough for any volatiles, water ice, carbon dioxide ice, methane, to start sublimating if they were present. Here's the thing about comets. When they get close to the Sun, they outgaze. Frozen materials on their surface absorb heat, turn into vapor, and jet outward, producing the iconic tails we associate with comets. That outgassing creates a reaction force, like a rocket engine, that pushes the comet slightly off course. This is called the non-gravitational effect, and it's well documented. Astronomers account for it when calculating comet orbits. But the non-gravitational effect requires visible gas and dust. It requires a coma, the fuzzy cloud around the nucleus. It requires spectroscopic signatures, emission lines from water, carbon monoxide, carbon dioxide that confirm the comet is actively venting material. 3I-ATLAS showed acceleration without obvious outgassing. There were no visible jets in the images, no prominent tail, no spectral lines strong enough to account for the magnitude of the acceleration. That's the anomaly. That's what has scientists arguing in conference rooms and on social media. Supporting the trajectory data is photometry, the measurement of brightness over time. A study titled Rapid Brightening of 3I-ATLAS Ahead of Perihelion, conducted by researchers including Zhang and Battams, tracked how the object's brightness changed as it approached the Sun. They found that brightness scaled with distance to the power of negative 7.5. To understand why that's strange, consider that most comets brighten at rates closer to negative 2 to negative 4, depending on how much dust and gas they produce. A steeper exponent means the object is brightening faster than expected, either because it's producing an unusual amount of reflective material, or because its surface properties are changing in unexpected ways. Spectroscopic observations add another layer. Earlier in its approach, the James Webb Space Telescope detected carbon dioxide in 3I-ATLAS's coma when the object was still far from the Sun. Carbon dioxide sublimates at lower temperatures than water ice, so detecting it early makes sense if the object is a comet. But as 3I-ATLAS got closer, the expected increase in water vapour, the hallmark of a comet near perihelion, didn't materialise in the magnitudes predicted. Some water was detected, but not enough to explain the acceleration or the rapid brightening. NASA's own fact sheets confirm the timeline. The object reached its closest point to the Sun on October the 29th and 30th at approximately 1.4 astronomical units, matching the perihelion window reported by JPL. The photometry, the trajectory data, and the spectroscopy all point to the same conclusion. Something unusual is happening, something that doesn't fit neatly into our existing models of comet behaviour. But models are just that, models. They're approximations built on assumptions. They assume certain compositions, certain surface properties, certain thermal responses. When an object behaves differently, it doesn't necessarily mean the object is artificial. It might just mean our assumptions are wrong. That's the argument the skeptics make, and it's a good argument. Science progresses by refining models, not by jumping to extraordinary conclusions. Still, the uncertainties are significant. Astrometric fits, the mathematical process of matching observed positions to predicted trajectories, come with error bars. Different assumptions about the object's mass, its surface reflectivity, its rotation rate, all feed into those calculations. Photometry depends on how you model the dust-to-gas ratio, the size distribution of particles, the albedo of the surface. Small changes in assumptions can produce large changes in interpretation. Here's an analogy that might help. Imagine you're watching a car drive down a highway. You know the speed limit, you know the engine size. You can calculate, based on physics, how fast the car should be going and where it should be at any given time. Now imagine the car starts accelerating without the driver pressing the gas pedal. No visible reason, no sound of the engine revving. The car just speeds up. You check your instruments, you check your assumptions. Maybe there's a hidden motor, maybe the road is tilted, maybe there's wind. But if you rule out all the natural explanations and the car keeps accelerating, you'd start to wonder, is there something else going on? Something you didn't account for? That's where we are with 3I-ATLAS, and the next observations, scheduled for early November and mid-December 2025, will either close the case or crack it wide open. Part 3. Loeb's interpretation versus natural hypotheses. Two competing frameworks dominate the debate. On one side, the natural explanation: outgassing and sublimation produce thrust, dust and gas emission cause brightness increases, and 3I-ATLAS is simply an extreme example of comet behaviour. On the other side, the speculative artificial origin, radiation pressure acting on a light sail, an internal propulsion system, or an engineered structure designed to manoeuvre through space. Both frameworks fit some of the data, neither fits all of it perfectly. Avi Loeb's reasoning starts with mass loss. If the acceleration is due to outgassing, if sublimating ice is producing the rocket effect that's pushing the object off course, then you can calculate how much mass the comet must be losing. The numbers are striking. To produce 135 kilometers per day squared of acceleration, a comet would need to vent a significant fraction of its total mass over the course of weeks or months. Loeb argues that such massive mass loss should be detectable. It should produce a visible gas plume, a prominent tail, and strong spectral signatures that instruments like the Hubble Space Telescope or the James Webb Space Telescope could easily detect. But those signatures haven't appeared, at least not in the magnitudes expected. Some carbon dioxide was detected earlier, some water vapour has been observed, but the emission levels are too weak to account for the acceleration. It's like watching a rocket lift off without seeing the exhaust plume. The effect is there, but the cause is missing. Loeb also points to the colour anomaly. Comets scatter sunlight, and the dust they produce typically absorbs blue wavelengths, making the reflected light appear reddish or neutral. But 3I-ATLAS appears blue. That's very surprising, Loeb says, because blue light suggests either extremely fine dust particles, much finer than typical cometary dust, or a reflective surface with properties more consistent with metal or engineered materials. Natural processes can produce fine dust, but not easily, and not in the quantities needed to explain both the brightness and the colour. So what could an artificial origin look like? One possibility is a light sail. Light sails are thin, reflective structures designed to be pushed by radiation pressure, the momentum carried by photons from a star. Scientists have proposed light sails as a way to propel spacecraft across interstellar distances without fuel. A sail large enough and light enough could, in theory, be accelerated by sunlight. As the sail approaches a star, radiation pressure increases, pushing the sail faster. Near perihelion, the effect would be strongest, producing exactly the kind of radial acceleration observed in 3I-ATLAS. The math is tricky, but not impossible. Radiation pressure at 1.36 astronomical units is weaker than at Earth's orbit, but it's still measurable. For a sail with the right area to mass ratio, thin enough, reflective enough, you could generate accelerations in the ballpark of what's been observed. The challenge is that such a sail would need to be incredibly thin, perhaps micrometers thick, and incredibly reflective, with an albedo close to 1. That's feasible for engineered materials, but unusual for natural objects. Another possibility is an internal propulsion system. Imagine a spacecraft that performs a burn near perihelion, using the sun's gravity to amplify its velocity change. This is a standard manoeuvre in orbital mechanics called a powered gravity assist. Human spacecraft do it all the time. You fire your engines at the point of closest approach to maximize the efficiency of the burn. If 3I-ATLAS was such a spacecraft, it might be executing a maneuver designed to alter its trajectory for some purpose we don't yet understand. Loeb calls this speculative, and he's right to. There's no direct evidence of an engine, no thermal excess, no exhaust signature. But absence of evidence isn't evidence of absence, especially when your instruments aren't designed to detect those signatures in the first place. Loeb has also suggested that 3I-ATLAS represents the 9th anomaly in the object's behaviour, implying it already has a list of unusual traits. He's been tracking this object closely, comparing it to Oumuamua, the first interstellar visitor, which also showed non-gravitational acceleration without obvious outgassing. The parallels are provocative. Both objects are interstellar. Both showed anomalous motion. Both lacked the clear cometary signatures you'd expect. One data point is an outlier. 2 data points are a pattern, and patterns demand explanation. But patterns can also mislead. Confirmation bias is a real risk in science. When you're looking for evidence of alien technology, it's easy to see it everywhere, even in data that has more mundane explanations. Critics of Loeb's approach point this out frequently. They argue that he's cherry-picking anomalies, ignoring data that doesn't fit his hypothesis, and overstating the implausibility of natural explanations. So what happens next depends on the observations scheduled for November and December 2025. If those observations detect strong outgassing, if they find water vapour and carbon monoxide in the quantities needed to explain the acceleration, then the natural explanation wins. 3I-ATLAS is just a weird comet, an extreme case, but ultimately natural. The case closes, and Loeb's speculation fades into the background. But if those observations don't find sufficient outgassing, if the acceleration continues without a visible source, then the artificial origin hypothesis becomes harder to dismiss. It moves from speculative fringe to serious possibility. And at that point, the conversation changes. We're no longer talking about comets and orbital mechanics. We're talking about contact, technology, intelligence, and what it means for humanity's place in the universe. Part 4. Controversy, institutional response and public reaction. The scientific community is not a monolith. It's a collection of individuals with different training, different biases, different tolerances for risk and speculation. When Avi Loeb suggests that an object might be alien technology, some researchers see a provocative thinker pushing boundaries. Others see a scientist abandoning rigour for headlines. Both views have merit, and both shape how the 3I-ATLAS controversy is unfolding. Mainstream comet scientists have been cautious. Many argue that the data, while unusual, doesn't yet justify extraordinary claims. Comets are complex. Their surfaces are heterogeneous. Pockets of volatile material can vent asymmetrically, producing jets that don't point directly away from the sun. Those jets can create torques that alter rotation rates, which in turn affect how the comet reflects light and how it accelerates. Modelling all of this requires detailed assumptions, and those assumptions come with uncertainties. Until we've exhausted natural explanations, the argument goes, we shouldn't invoke alien technology. That's a reasonable position. Science is conservative by design. Extraordinary claims require extraordinary evidence, and the evidence for 3I-ATLAS being artificial isn't yet extraordinary. It's suggestive. It's intriguing. But suggestive and intriguing aren't the same as conclusive. Yet there's another dimension to this controversy that has nothing to do with the data. It has to do with institutional behaviour, transparency, and trust. Loeb has publicly accused NASA of delaying or withholding certain observations. Specifically, he's claimed that an image taken by the High-Resolution Imaging Science Experiment on the Mars Reconnaissance Orbiter on October 2nd, 2025 has not been released. HiRISE is capable of capturing extremely detailed images, and if it pointed at 3I-ATLAS during the object's approach, that image could contain critical information about the object's surface, its shape, its reflectivity, and whether it shows any features inconsistent with a natural comet. NASA has not publicly addressed this specific claim. That silence has fueled speculation. On social media, conspiracy theories have proliferated. Some users suggest that NASA is suppressing evidence because the object is indeed artificial, and the agency doesn't want to cause public panic. Others argue that the delay is bureaucratic, that image releases go through standard review processes, and that there's nothing sinister about it. The truth is probably somewhere in between. Space agencies are cautious about releasing data that might be misinterpreted. They're also cautious about releasing data before it's been properly calibrated and vetted. But that caution can look like obfuscation, especially when high-profile scientists are publicly calling for transparency. Adding fuel to the fire is NASA's public messaging. In late October, NASA's acting administrator responded to a question from a prominent internet figure, reportedly Kim Kardashian, though the details vary depending on the source, about whether 3I-ATLAS posed a threat or was alien in origin. The administrator's response was blunt. No aliens. No threat. That statement was meant to reassure the public, but it had the opposite effect on some audiences. To critics, it sounded dismissive, like NASA was downplaying legitimate scientific questions to avoid controversy. This tension between transparency and caution is not new. Space agencies have always walked a fine line when it comes to anomalies that might have extraordinary explanations. They don't want to fuel conspiracy theories, but they also don't want to appear as though they're hiding information. The problem is that in the age of social media, every decision is scrutinized, every delay is questioned, and every statement is dissected for hidden meaning. The International Asteroid Warning Network, a coalition of space agencies and observatories, activated a comet campaign in response to 3I-ATLAS. The campaign, running from November 2025 through January 2026, is designed to coordinate observations from multiple telescopes and instruments, pooling data to get the clearest possible picture of what the object is and how it's behaving. On the surface, this sounds like standard scientific procedure: unusual object, coordinated response, rigorous analysis. But some interpret the activation of the campaign as evidence that agencies are taking the anomaly seriously, perhaps more seriously than they're willing to admit publicly. Why activate a coordinated campaign for a comet unless you think there's something worth investigating? Why involve so many telescopes and less? The stakes are higher than routine. Public perception has shifted rapidly. Before October, 3I-ATLAS was a minor footnote in the astronomy community, one of several interstellar objects detected in recent years. Now it's a cultural moment. It's trending on social media. It's being discussed in podcasts, YouTube videos, and news articles. People are asking questions. Are we alone? Is this the moment everything changes? Do we trust NASA? That last question is the most dangerous. Trust in institutions is fragile. When people feel that information is being managed or withheld, they fill the gaps with speculation, and speculation can spiral into distrust. Scientists like Loeb, who are willing to publicly question institutional narratives, become lightning rods. They're celebrated by some as truth-tellers and criticized by others as attention seekers. The reality, as always, is more nuanced. What happens if the evidence leans toward artificial origin? That's the scenario no one wants to talk about publicly, but everyone is thinking about privately. If 3I-ATLAS turns out to be a piece of alien technology, the implications are staggering. Policymakers would get involved. SETI-style oversight might be activated. Governments would have questions. Is it a probe? Is it active? Is it a threat? Is it an opportunity? And if that scenario unfolds, the conversation we're having right now about comets and orbital mechanics will seem quaint in retrospect. Part 5. Immediate stakes and upcoming observations. The timeline for the next few months is critical. Everything hinges on observations scheduled for November and December 2025. These aren't casual follow-ups. These are targeted campaigns involving some of the most powerful telescopes and instruments humanity has ever built. What they find will either close the 3I-ATLAS case or open it wider than anyone is prepared for. The European Space Agency's JWST mission is first in line. JWST stands for Jupiter Icy Moons Explorer, and it's currently en route to Jupiter, where it will study Europa, Ganymede, and Callisto. But trajectories are funny things. Sometimes spacecraft pass near objects of interest purely by chance, and in early November 2025, JWST is predicted to pass relatively close to 3I-ATLAS. According to orbital calculations, the flyby distance will be approximately 0.428 astronomical units, or about 64 million kilometres. That's not close in human terms, but in space terms it's practically a near miss. JWST carries cameras and spectrometers. If the flyby geometry is favourable, it could capture images of 3I-ATLAS with higher resolution than anything we've seen so far. It could analyse the spectrum of reflected sunlight, looking for signatures of specific molecules or materials. If 3I-ATLAS is outgassing, JWST might detect it. If the object has unusual surface, features, facets, structures, reflective patches, JWST might see them. Avi Loeb has been vocal about the importance of the JWST observations. He's predicted that if 3I-ATLAS is a natural comet, JWST should detect clear signs of gas emission, water vapour, carbon monoxide, maybe ammonia or methanol. If those signatures are present in the quantities needed to explain the acceleration, the natural explanation is vindicated. If they're absent or too weak, the artificial origin hypothesis gains credibility. Later in December, around the 19th, the Hubble Space Telescope and the James Webb Space Telescope are both scheduled to observe 3I-ATLAS. Hubble excels at visible and ultraviolet wavelengths, perfect for detecting gas emission lines and measuring how light scatters off the object's surface. JWST operates in the infrared, ideal for detecting thermal emission and looking for heat signatures that might indicate internal activity or unusual surface properties. These observations will be more sensitive than anything that came before. If there's gas around 3I-ATLAS, Hubble and JWST will find it. If there's dust, they'll measure its composition and size distribution. If there are thermal anomalies, hot spots, cold spots, asymmetries, they'll map them. The data will be analysed by multiple independent teams, ensuring that no single interpretation dominates without scrutiny. Ground-based observatories are also involved. Telescopes in Chile, Hawaii and the Canary Islands are all part of the coordinated campaign. Spectroscopic observations will track changes in the object's light over time, looking for periodic variations that might indicate rotation or surface features passing in and out of view. Photometric monitoring will measure brightness changes, refining the models of how the object reflects sunlight. The outcomes fall into two broad categories. Outcome A is that the observations detect sufficient outgassing and dust production to explain both the acceleration and the brightness anomaly. In this scenario, 3I-ATLAS is confirmed as a natural comet, albeit an unusual one. Scientists publish papers analysing its composition, its activity patterns, and what makes it different from other comets. The case becomes a footnote in the history of interstellar objects, interesting, instructive, but ultimately not revolutionary. Outcome B is that the observations don't find enough gas or dust to explain the acceleration. The object continues to accelerate without a visible source of thrust. Spectroscopic analysis reveals surface properties inconsistent with typical comets. Thermal imaging detects anomalies. In this scenario, the artificial origin hypothesis moves from speculative to plausible. Scientists start asking harder questions. Mission proposals get drafted. SETI researchers get involved. Policymakers get briefed. If outcome B occurs, the follow-up could include targeted missions. Proposals might be fast-tracked for spacecraft to intercept 3I-ATLAS while it's still within reach. A flyby mission could capture close-up images, measure the object's mass and density, analyse its surface in detail. A rendezvous mission could orbit the object, studying it over weeks or months. If the object is truly artificial, such missions would be among the most important scientific endeavours in human history. There's also the question of what happens to public perception. If the evidence leans artificial, trust in institutions will be tested. People will want answers. They'll want to know what governments knew, when they knew it, and why the information was or wasn't shared. The media will amplify the story. Social media will explode with theories, debates, and demands for transparency. This moment is a fork in the road for modern astronomy. For decades, we've searched for signs of intelligent life beyond Earth. We've pointed radio telescopes at the stars, listening for signals. We've analysed exoplanet atmospheres, looking for biosignatures. We've built frameworks for detecting technosignatures, megastructures, Dyson spheres, laser pulses, anything that might indicate the presence of advanced civilizations. But we've always assumed that if we found something, it would be far away, light years distant, safe and abstract. 3I-ATLAS is not far away. It's here. It's in our solar system. It's close enough to study, close enough to reach, close enough to force us to confront the possibility that we are not alone, and that the evidence has been drifting past us all along, waiting for someone to look closely enough. The next few months will tell us whether that's the case. Either we close the book on 3I-ATLAS and return to business as usual, or we open a new chapter in human history, one where the cosmos is no longer empty, but full of minds and machines and questions we're only beginning to learn how to ask. And now we've seen the claim, the data, and what's at stake. Next we go deeper. Hidden trajectories, brightness mysteries, conspiracies, physics, and what-if scenarios that push the boundaries of what we think is possible. Part 6. Trajectory and kinematic context. To understand where 3I-ATLAS came from, you have to understand what interstellar space looks like. The galaxy is not empty. Between the stars there are clouds of gas and dust, rogue planets, ejected comets, and debris from stellar collisions. Objects drift through this interstellar medium for millions or billions of years, moving under the gravitational influence of distant stars, their trajectories shaped by the slow waltz of galactic dynamics. Most of these objects will never encounter another star. They'll wander forever in the dark, but occasionally one gets close enough to a star like our Sun to be captured temporarily by its gravity, swinging through the solar system on a hyperbolic trajectory before heading back into the void. 3I-ATLAS is the third such object we've confirmed. The first was Oumuamua, discovered in 2017. The second was Comet Borisov, discovered in 2019. Both were immediately recognisable as interstellar because their orbits were hyperbolic, meaning they were moving faster than the escape velocity of the solar system. They weren't bound to the Sun, they were just passing through. Population models suggest that interstellar objects like these are common. A paper by Hopkins and Dorsey titled From a Different Star estimated that at any given time there are likely thousands of interstellar objects within the orbit of Neptune, most too small or too faint to detect with current telescopes. That means we're not seeing rare visitors, we're seeing the tip of an iceberg, the brightest and closest examples of a phenomenon that's happening constantly, all around us unnoticed. 3I-ATLAS has a velocity at infinity, the speed it would have if the Sun's gravity weren't affecting it, of approximately 20 to 30 kilometers per second, depending on the exact orbital solution. That's fast by solar system standards, but typical for interstellar objects. Its orbital inclination, the angle at which its path tilts relative to the plane of the solar system, is high, around 70 to 80 degrees. That's another hallmark of interstellar origin. Solar system objects tend to orbit in the same plane because they formed from the same protoplanetary disk. Interstellar objects come from random directions, their inclinations reflecting the chaotic dynamics of the galaxy. Where did it come from? That's harder to pin down. You can trace the trajectory backward, accounting for the sun's gravity and the gravitational influence of the planets. But once you extend the path into interstellar space, uncertainties grow. Small errors in the measured velocity or position compound over time. Still, researchers have tried. Some models suggest 3I-ATLAS originated in the thin disk of the Milky Way, the region where most stars and planetary systems reside. Others suggest the thick disk, an older, more diffuse population of stars with different kinematics. The thick disk hypothesis is intriguing because it implies the object could be billions of years old, a relic from an earlier epoch of the galaxy. Could it have passed near other stars? Almost certainly. Over billions of years, an object drifting through the galaxy will encounter stellar neighbourhoods, passing within a few light years of dozens or hundreds of stars. Each encounter tweaks the trajectory slightly. Over enough time, the original orbit is erased, replaced by a path shaped by countless gravitational nudges. If 3I-ATLAS is artificial, that history raises questions. Was it sent deliberately? Did it launch from a star we could identify? Or has it been wandering so long that its origin is lost? There's also the question of spacecraft. Humanity has sent several probes into interstellar space or on trajectories that will eventually leave the solar system. Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, New Horizons. All of them are travelling slower than 3I-ATLAS. If 3I-ATLAS is artificial, it's moving faster than anything we've built, implying either a more advanced propulsion system or a longer period of acceleration, perhaps a light sail pushed by starlight over centuries or millennia. The JWST flyby in early November adds another layer of interest. JWST is travelling through space on its way to Jupiter, and its trajectory happens to bring it relatively close to 3I-ATLAS. Relative, of course, is a matter of perspective. 0.428 astronomical units is about 64 million kilometres, far too distant for detailed imaging with JWST's cameras, but close enough for spectroscopy if the geometry and timing are right. JWST wasn't designed to study interstellar objects, but sometimes serendipity offers opportunities, and this is one of them. If 3I-ATLAS passes through regions of interesting plasma or magnetic field environments, that could also matter. The solar wind, the stream of charged particles flowing outward from the sun, interacts with any object in its path. If the object has a magnetic field or a charged surface, that interaction can produce detectable signatures. If 3I-ATLAS is artificial, if it's a spacecraft with conductive materials, the solar wind might create a wake or disturbance that differs from what you'd expect for a natural comet. There's also the trajectory crossing near other spacecraft. Mars orbiters, for example, have imaged comets in the past. The Mars Reconnaissance Orbiter, with its high-rise camera, is capable of extraordinary resolution. If it pointed at 3I-ATLAS during the object's approach, it could have captured details invisible to ground-based telescopes. Whether such an image exists and whether it's been released is part of the ongoing controversy. The orbital path of 3I-ATLAS also matters for future observations. As the object moves away from the sun, it will fade. Reflected sunlight diminishes with distance, and eventually even the largest telescopes will struggle to detect it. That means the observation window is closing. If we don't learn what we need to learn in the next few months, the object will slip beyond reach. Another mystery fading into the dark. But here's the speculative edge. If 3I-ATLAS is artificial, if it was sent from a thick disk exoplanet system billions of years ago, then its passage through our solar system might not be random. It might be one of many. We might be looking at a single data point in a much larger pattern, a pattern we'll only recognise once we've detected enough interstellar objects to see the distribution, the trajectories, the statistical fingerprints of intentional voyages rather than random drift. And that thought brings us to a question that should keep you awake at night. How many of these objects have we missed? How many passed through the inner solar system before we had the telescopes to see them? How many are out there right now, too faint or too far to detect, carrying information or technology, or simply drifting as monuments to civilizations long extinct? The trajectory of 3I-ATLAS is not just a line through space, it's a thread connecting us to the possibility that the galaxy is not silent, not empty, but full of travellers like this one, and we're only now learning how to see them. Part 7. Brightness Law. Anomalies and photometry detail. Numbers tell stories if you know how to read them. The brightness of 3I-ATLAS follows a power law. Brightness is proportional to distance raised to the power of negative 7.5. Written mathematically, that's brightness equals some constant times distance to the negative 7.5. For those not fluent in mathematical notation, what this means in plain language is that as the object gets closer to the Sun, it gets brighter much faster than you'd expect for a typical comet. Most comets brighten as they approach the Sun, but the relationship is gentler, usually following an exponent somewhere between -2 and -4. An exponent of -2 means brightness increases with the square of decreasing distance. An exponent of -7.5 means brightness increases with nearly the 8th power of decreasing distance. That's not a small difference. That's a dramatic difference, the kind that makes astronomers stop and ask, what's going on here? Several physical mechanisms could explain super steep brightening. One possibility is very fine dust particles. When sunlight scatters off particles, the efficiency of scattering depends on particle size. Smaller particles scatter light differently than larger ones. If 3I-ATLAS is producing extremely fine dust, particles measured in micrometers rather than millimeters, that could increase the brightness more rapidly than standard models predict. But producing fine dust requires fragmentation, collisions, or sublimation processes that break larger grains into smaller ones. That usually happens when a comet is very active, venting large amounts of gas and dust. But 3I-ATLAS doesn't show the gas signatures you'd expect for such high activity. Another possibility is rapid sublimation of volatile species. Carbon dioxide ice sublimates at lower temperatures than water ice, so as a comet approaches the Sun, carbon dioxide can begin venting before water does. If 3I-ATLAS is rich in carbon dioxide, or if it contains other volatiles like carbon monoxide or methane, those materials could be driving the brightness increase. Early observations with the James Webb Space Telescope did detect carbon dioxide in the coma, when the object was farther from the Sun, supporting this idea. But again, the amount of gas detected doesn't seem sufficient to explain both the brightness curve and the acceleration. There's also thermal fracturing. As a comet heats up, thermal stress can crack the surface, exposing fresh ice underneath. Fresh ice is more reflective than weathered ice, so exposing new material could cause a sudden increase in brightness. This mechanism has been observed in other comets, particularly those with layered or heterogeneous surfaces. But thermal fracturing usually produces brightness spikes that are temporary. The object brightens suddenly, then stabilizes or dims as the newly exposed ice sublimates away. The brightness curve of 3I-ATLAS seems more consistent with a sustained process rather than a one-time event. And then there's the speculative alternative, internal heating or controlled reflection. If 3I-ATLAS has an internal energy source, something generating heat from within, like a decaying power source or an active engine, that could warm the surface in ways that don't match solar heating alone. Alternatively, if the object has a reflective surface with unusual properties, perhaps engineered to maximize or minimize light reflection at certain wavelengths, that could produce a brightness curve that doesn't fit natural models. Comparing 3I-ATLAS to other interstellar objects is instructive. Oumuamua, the first interstellar visitor, showed no coma, no tail, no obvious signs of outgassing. Yet it also exhibited non-gravitational acceleration, leading Loeb and others to suggest it might be a light sail or a fragment of one. Comet Borisov, the second interstellar object, behaved much more like a typical comet. It had a visible coma, a tail, and spectroscopic signatures consistent with water and carbon monoxide. It brightened as it approached the Sun, but the brightness curve followed more conventional exponents. 3I-ATLAS sits somewhere between these two extremes. It shows some gas, some activity, but not enough to explain its acceleration or its rapid brightening. It's anomalous without being completely alien, at least not yet. Colour indices add another dimension to the puzzle. Photometry doesn't just measure brightness, it measures brightness at different wavelengths. By comparing how bright an object appears in blue light versus red light, astronomers can infer properties about the surface or the dust. Typical comets have slightly red colour indices because their dust preferentially scatters longer wavelengths. But 3I-ATLAS appears unusually blue. Blue colour suggests either very small particles which scatter blue light efficiently, or a reflective surface with high albedo in the blue part of the spectrum. Observations from the 3I telescope and the JWST instrument, among others, have measured colour magnitude differences and confirmed the blue hue. That's not impossible for a natural comet, but it's unusual. Combine the blue colour with the steep brightness curve and the lack of strong gas emission, and you start to see why some scientists are intrigued and others are sceptical. Each anomaly by itself could have a natural explanation. Together they form a pattern that's harder to dismiss. Recent papers on ARXIV, the preprint repository for scientific research, include measurements of water production rates at distances greater than 3 astronomical units. Water sublimate at temperatures that correspond to distances closer to the Sun, so detecting water early suggests either very efficient heating or pockets of volatile-rich material exposed on the surface. But the detected water production rates, while notable, are not large enough to account for the acceleration observed near perihelion. That gap between expected and observed behaviour is the heart of the mystery. Here's where speculation becomes irresistible. What if the brightness spike is not due to dust or gas, but to the exposure of metallic surfaces? If 3I-ATLAS is a fragment of technology, a broken sail, a defunct probe, a piece of debris from some ancient collision, it might have reflective materials that don't behave like ice or rock. Metals, especially polished or engineered surfaces, have high albedo and reflect light in ways that depend on the angle of incidence and the wavelength of light. A tumbling object with metallic facets could produce brightness variations that don't fit comet models. Or consider internal light. This is the wildest speculation, but if 3I-ATLAS has an internal energy source, if it's still partially operational after however many millions or billions of years it's been travelling, that energy could manifest as heat or light. A spacecraft with a decaying power source might emit infrared radiation detectable by telescopes like JWST. A probe with failing systems might have hotspots, where electronics are still drawing power. These are not ideas you propose lightly in a peer-reviewed journal, but they're ideas you think about late at night when the data refuses to fit the models you trust. The brightness anomalies are not proof of anything. They're clues. They're the breadcrumbs that lead you deeper into the forest, wondering if you're following a path toward discovery or getting lost in a maze of coincidences. Part 8. Conspiracies, Data Transparency and Biases. What if the reason we're surprised by 3I-ATLAS is not because the object is surprising, but because we haven't seen all the data? What if there are images, spectra, measurements sitting on servers somewhere, reviewed by a handful of scientists, withheld from public release for reasons that range from bureaucratic to sinister, depending on who you ask? Avi Loeb has publicly stated that NASA withheld imagery from the Mars Reconnaissance Orbiter. Specifically, he claims that HiRISE, the high-resolution camera on the orbiter, captured an image of 3I-ATLAS on October 2, 2025, and that this image has not been released. HiRISE is one of the most powerful cameras in space, capable of resolving features as small as a meter across on the Martian surface. Pointed at an interstellar object, it could reveal details invisible to ground-based telescopes, surface texture, shape, possibly even structures or features that would settle the question of natural versus artificial origin. Why would such an image be withheld? There are several possible explanations, and they span a spectrum from mundane to conspiratorial. The mundane explanation is that image releases go through standard calibration and review processes. Raw data from spacecraft instruments is not immediately published. It's processed, checked for errors, calibrated against known standards and reviewed by science teams before release. This process can take weeks or months. It's not a cover-up, it's standard procedure. The less mundane explanation is that the image reveals something controversial, something that requires careful interpretation before public release. If the image shows anomalies, features that don't fit the profile of a comet, NASA might delay release until those anomalies are understood, to avoid fueling speculation or misinterpretation. This isn't necessarily malicious. Space agencies have been burned before by releasing data that was misinterpreted by the public or the media, leading to false narratives that are hard to correct once they've taken root. The conspiratorial explanation is that NASA knows 3I-ATLAS is artificial and is managing the narrative to avoid panic or disruption. This explanation is popular in certain corners of the internet, but it's also the least plausible. Space agencies are not monolithic. They're staffed by thousands of scientists, engineers and administrators, many of whom would not go along with suppressing evidence of alien technology. Leaks would be inevitable. Moreover, the scientific community operates on principles of transparency and peer review. Withholding data undermines those principles and risks careers. It's hard to imagine a scenario where such a conspiracy could hold. Still, the perception of withholding data is almost as damaging as actual withholding. When scientists like Loeb publicly call for transparency and don't receive clear responses, it feeds distrust. People start asking, what are they hiding? Why aren't they showing us everything? And once those questions take root, they're hard to dislodge. The International Asteroid Warning Network announced a comet campaign running from November 2025 through January 2026. IARN is a coalition of space agencies and observatories designed to coordinate responses to potentially hazardous asteroids and comets. Activating a campaign for 3I-ATLAS makes sense if the object is unusual enough to warrant coordinated observation, but it also raises eyebrows. Is this simply standard protocol for an anomalous interstellar object, or is it evidence that agencies are more concerned than they're letting on? Institutional incentives play a role here. Space agencies depend on public trust and government funding. If they prematurely speculate about alien technology and turn out to be wrong, they risk their credibility. Politicians might question funding decisions. The media might portray them as reckless. But if they're too conservative, too cautious in acknowledging anomalies, they risk being accused of hiding information or ignoring important questions. It's a tightrope walk, and 3I-ATLAS is testing their balance. Peer review and scientific caution are essential, but they can also function as gatekeeping. When an idea challenges the mainstream, it faces higher scrutiny, which is appropriate. Extraordinary claims require extraordinary evidence, but there's a risk that conservatism becomes reflexive, that anomalies are explained away not because the explanations are good, but because the alternatives are uncomfortable. Confirmation bias works both ways. You can be biased towards seeing aliens everywhere, or biased toward never seeing them even when they're staring you in the face. Some mainstream comet and orbital dynamics experts have criticized Loeb's approach. They argue that he's cherry-picking anomalies, focusing on data points that support his hypothesis while ignoring others that don't. They point out that comet activity is complex, that models have uncertainties, and that jumping to artificial explanations before exhausting natural ones is premature. These are fair criticisms. Science progresses by testing hypotheses rigorously, not by leaping to conclusions. But there's also the question of what counts as exhausting natural explanations. How many models do you try before you consider alternatives? How weak do the natural explanations have to be before speculation becomes justified? There's no clear answer, and that ambiguity is where the controversy lives. Speculation about internal memos and unpublished data is inevitable. Maybe there are higher resolution images that haven't been released. Maybe there are spectroscopic observations that show unexpected features. Maybe there are internal discussions among scientists weighing how to present the findings without causing misinterpretation. Or maybe there's nothing. No conspiracy, no hidden data. Just the slow grind of scientific process and the natural delays of bureaucracy and peer review. The grainy quality of released images from Punch has also been questioned. Are the images grainy because the instrument has limited resolution, or because someone chose to release lower quality versions? The former is more likely. Punch's wide-field imager was designed to study the Sun's corona, not faint interstellar objects. Imaging, 3I-ATLAS stretched the instrument to its limits. The graininess is probably a reflection of those limits, not intentional obfuscation. Transparency in science is critical, but it's also messy. Scientists work with incomplete data, uncertain models, and the pressure to be both rigorous and timely. When anomalies appear, the temptation to speculate is strong, but so is the risk of being wrong. Institutions try to balance these pressures, but balance is hard, and in the age of social media, every decision is scrutinized, every delay questioned, every statement parsed for hidden meaning. If there is bias or delay, what might it hide? And what could the physics look like if we let our imaginations run wild, unconstrained by conservatism or caution? Part 9. Physics and Engineering Hypotheses. Assume for a moment that 3I-ATLAS is artificial. Set aside skepticism and conservatism and ask, what could it physically be? What engineering principles could explain the acceleration, the brightness, the colour, the trajectory? This is speculation, but it's informed speculation, grounded in physics and constrained by the data. Start with a light sail. Light sails are not science fiction. They're a real concept, proposed by scientists and engineers as a method for interstellar travel. The idea is simple. Photons carry momentum. When light hits a reflective surface, it transfers that momentum, producing a tiny but measurable force. A sail with a large area and low mass can be accelerated by starlight over time, eventually reaching speeds that would take conventional rockets enormous amounts of fuel to achieve. For a light sail to produce the acceleration observed in 3I-ATLAS, you need the right area to mass ratio. The object would need to be thin, perhaps only micrometers thick, and highly reflective, with an albedo close to 1. Materials like aluminized mylar or carbon fiber composites could achieve this. At 1.36 astronomical units, the intensity of sunlight is weaker than at Earth's orbit, but it's still strong enough to push a sufficiently large and light sail. Run the numbers. Radiation pressure at 1.36 astronomical units is approximately 4.5 micronewtons per square metre for a perfectly reflective surface. To produce an acceleration of 135 kilometers per day squared, which converts to roughly 1.56 times 10 to the negative 4 meters per second squared, you need a specific area to mass ratio. If the sail has an area of, say, 1 square kilometre and a mass of a few hundred kilograms, the numbers start to work out. That's a thin sail, but not impossibly thin. The catch is that such a sail would need to survive interstellar space for potentially millions or billions of years. Cosmic rays, micrometeorites, and interstellar dust would erode the surface. The sail might be tattered, torn, or partially degraded by the time it reaches our solar system. That degradation could explain why the object doesn't behave exactly like a pristine sail. It might be tumbling, reflecting light asymmetrically, producing acceleration in directions that depend on its orientation relative to the Sun. Another possibility is an internal propulsion system. Spacecraft performing gravity assist maneuvers often fire their engines at perihelion, the point of closest approach to the star or planet they're using for the assist. Firing at perihelion maximizes the efficiency of the burn because the spacecraft is moving fastest at that point, and the Oberth effect amplifies the change in velocity. If 3I-ATLAS were a spacecraft executing a powered gravity assist, it might fire an engine near perihelion to alter its trajectory. What kind of engine? Chemical rockets are unlikely. They require fuel, and carrying enough fuel for a burn that lasts days or weeks would require a large mass, inconsistent with the observed acceleration. Electric propulsion, like ion drives, could work. Ion drives produce low thrust over long periods, accelerating slowly but efficiently. But ion drives require power, typically from solar panels or nuclear reactors. A spacecraft with a degraded power system might still be capable of low-thrust maneuvers. Alternatively, consider exotic propulsion. If the object is from an advanced civilization, it might use technologies we don't understand. Maybe it manipulates electromagnetic fields. Maybe it uses some form of reactionless drive, though such drives would violate conservation of momentum as we understand it. This is wild speculation, bordering on fantasy. But if we're entertaining the idea of alien technology, we can't rule out technologies beyond our current physics. What about materials? If 3I-ATLAS is artificial, what is it made of? Metals would explain the blue colour and high reflectivity. Aluminum, titanium, or more exotic alloys could have the necessary strength to mass ratios. Carbon composites are another option, lightweight and strong, capable of surviving harsh environments. Some materials might exhibit unusual thermal properties, reflecting or emitting light in ways that don't match natural objects. Spectroscopy could reveal material signatures. Metals have characteristic absorption and emission lines. If 3I-ATLAS reflects sunlight with a spectrum that shows metallic absorption features, that would be a smoking gun. So far, published spectra haven't shown such features, but the resolution and signal-to-noise of those spectra may not be sufficient to detect weak lines. Thermal infrared observations are another avenue. If the object has an internal heat source, it would emit more infrared radiation than expected for a passive object heated only by the sun. JWST, with its infrared sensitivity, could detect such excess emission. If the observations in December reveal thermal anomalies, that would strengthen the artificial hypothesis. There's also the question of purpose. If 3I-ATLAS is artificial, why is it here? Is it a probe sent to study our solar system? Is it a derelict, a piece of ancient technology long since defunct? Is it part of a network, a fleet of similar objects scattered across the galaxy, monitoring or mapping stellar systems? Loeb has used the metaphor of a Trojan horse, something that appears benign but might carry hidden payloads or functions. That metaphor is provocative, even ominous, but it's worth considering. Could the object be sending smaller probes? Could it be dropping instrumentation as it passes through the solar system? There's no evidence for this, but absence of evidence is not evidence of absence. If such probes exist and are small enough, they would be nearly impossible to detect with current telescopes. Engineering a device that survives billions of years in interstellar space is no small feat. Radiation damage, thermal cycling, micrometeor impacts, all of these would degrade materials over time. Any civilization capable of building such a device would need to account for degradation, perhaps by over-engineering the structure or using self-repairing materials. The fact that 3I-ATLAS is still functioning, if it is, suggests either recent origin or extraordinarily durable construction. This line of reasoning leads to philosophical territory. If 3I-ATLAS is artificial and functional, it implies a civilization capable of interstellar travel, or at least interstellar messaging. It implies they've been around long enough to send such objects into the galaxy. It implies we're not alone, and more than that, it implies they're interested, or were interested, in places like our solar system. And that thought opens the door to implications that go far beyond orbital mechanics and photometry. Part 10. Philosophical and Scientific Culture. Implications. If 3I-ATLAS is artificial, what does that mean? Not just for astronomy, not just for our understanding of comets and interstellar objects, but for humanity's place in the cosmos, for our sense of who we are and what we might become. Start with the statistical question. The galaxy contains hundreds of billions of stars. Many of those stars have planets. Some of those planets are in habitable zones. Some fraction of habitable planets might develop life. Some fraction of those might develop intelligent life. Some fraction of intelligent civilizations might develop technology capable of interstellar travel or at least interstellar communication. The Drake equation formalizes this chain of reasoning, though the values of its terms are uncertain. But even conservative estimates suggest there should be many technological civilizations in the galaxy. So where are they? That's the Fermi paradox. If intelligent life is common, why haven't we seen evidence of it? Why haven't we detected radio signals, megastructures, Dyson spheres, or fleets of spacecraft? One answer is that we haven't looked hard enough, or we've been looking in the wrong ways. Another answer is that intelligent civilizations are rare, short-lived, or self-destructive, and we're alone or nearly alone in the galaxy. A third answer is that they're here, or their artifacts are here, and we've been missing them because we didn't know what to look for. 3I-ATLAS, if artificial, would shift the balance of that debate. It would suggest that technological artifacts are not rare. It would suggest that civilizations send objects into the galaxy, whether as probes, messages, or simply as debris from their activities. It would suggest that the Fermi paradox has an answer, and the answer is, they're everywhere. We've just been looking past them. SETI, the search for extraterrestrial intelligence, has focused primarily on radio and optical signals. Researchers have scanned the sky for narrow-band radio transmissions or laser pulses that might indicate intentional communication. But techno's signatures could take many forms. Megastructures like Dyson spheres would block starlight in characteristic ways. Atmospheric pollutants from industrial civilizations might show up in exoplanet spectra. And interstellar probes or debris might pass through our solar system, accelerating in ways that gravity alone can't explain. Loeb has been a vocal advocate for expanding SETI to include searches for physical artifacts. He's argued that we should treat anomalous objects seriously, that we should investigate them with the same rigour we apply to radio CT, and that dismissing them out of hand is a failure of scientific imagination. His critics argue that he's lowering the bar for evidence, that he's willing to entertain extraordinary explanations without sufficient data. Both perspectives have merit. The tension between them reflects a broader question about how science should respond to anomalies. Scientific conservatism has value. It prevents false positives. It ensures that claims are tested rigorously before being accepted. But conservatism can also become dogma. It can create an environment where certain questions are off limits, where researchers who ask those questions are marginalised or ridiculed. Loeb's willingness to push boundaries, to ask uncomfortable questions, challenges that conservatism. Whether he's right about 3I-ATLAS remains to be seen, but his approach has already shifted the conversation. What would happen if 3I-ATLAS were confirmed as artificial? Policymakers would get involved. Governments would want to know, is it a threat? Is it still operational? Can we communicate with it? Can we retrieve it? National security agencies might take an interest. The object might be classified, its data restricted. Or it might become a focal point for international cooperation, a shared discovery that transcends borders. Funding for astronomy and SETI would likely increase. If one interstellar artifact has been found, there might be others. Telescopes would be tasked with searching for similar objects. Mission proposals for intercept or rendezvous would be drafted. The scientific community would mobilise in ways it hasn't since the Apollo era. The cultural impact would be enormous. Religion, philosophy and worldview would all be challenged. Some religious traditions might embrace the discovery, seeing it as confirmation of a cosmos full of creation. Others might struggle with the implications. Philosophers would debate what it means for human significance if we're not unique. Existential risk researchers would ask, if civilizations send probes, do they also send weapons? Is the galaxy safe, or are we naive to assume benign intentions? Loeb has invoked the dark forest analogy elsewhere, borrowed from science fiction. The idea is that the galaxy might be a dangerous place, where civilizations hide to avoid detection by potentially hostile neighbours. If that's true, then finding evidence of other civilizations is not just a scientific milestone, but a potential existential risk. We might be announcing our presence to entities that would prefer we remain silent. That's speculative, perhaps overly pessimistic, but it's a question worth asking. Contact scenarios range from benign to catastrophic. A defunct probe tells us someone else is or was out there, but doesn't pose immediate risk. An operational probe raises questions about intent. A hostile artifact is the nightmare scenario, but also the least likely given the immense distances and timescales involved. Public trust in science and institutions would be tested. If the discovery is handled transparently, if data is shared openly, if the process is rigorous and inclusive, it could strengthen trust. But if there's perceived secrecy, if information is managed or spun, it could deepen cynicism and distrust. The way we handle 3I-ATLAS, regardless of what it turns out to be, will set precedents for how we handle future anomalies. Before we leap fully into the unknown, let's step aside and look at what else is happening in the frontier of science and artificial intelligence. Because 3I-ATLAS may be just the beginning of a new era, one where the boundaries between natural and artificial, between discovery and detection, between what we know and what we're about to learn, are blurring faster than we can keep up. Part 11. Recent comet event. Comet C2025 R2 SWAN. While 3I-ATLAS has captured headlines, another comet made a close approach to the Sun in late October 2025. Comet C2025 R2, discovered by the Solar and Heliospheric Observatory's SWAN instrument, provides a useful comparison case. If you want to understand whether 3I-ATLAS is genuinely anomalous, you need a control, a typical comet behaving in typical ways so you can measure the difference. Comet SWAN approached the Sun on a trajectory that brought it within about 0.8 astronomical units, closer than 3I-ATLAS but still outside Earth's orbit. As it neared perihelion, it brightened, developed a visible coma and tail, and exhibited all the characteristics astronomers expect from a sun-grazing comet. Photometric, observations tracked its brightness over time, and the curve followed a more conventional power law, with an exponent closer to -3, well within the range of normal comet behaviour. Spectroscopic observations of SWAN detected water vapour, carbon monoxide, and dust. The gas production rates matched models for a comet of its estimated size and composition. There were no surprises. The object behaved exactly as cometary physics predicts. Ice sublimates under solar heating, gas jets produce thrust, dust scatters sunlight, and the brightness increases in proportion to the amount of material vented. Comparing SWAN to 3I-ATLAS highlights the differences. SWAN showed strong gas emission. 3I-ATLAS did not. SWAN's brightness curve followed conventional models. 3I-ATLAS's brightness curve was steeper. SWAN's colour was typical for comets. 3I-ATLAS appeared unusually blue. Each of these differences, taken individually, might be explained by variations in composition, structure, or activity patterns. But taken together, they paint a picture of two very different objects. One interpretation is that 3I-ATLAS is simply an extreme case, a comet with unusual properties that push the boundaries of what's possible within natural processes. Comets are diverse. They form in different regions of protoplanetary disks, accrete different materials, experience different thermal histories. Some are water-rich, others carbon dioxide-rich. Some have porous, fluffy structures, others are dense and compact. It's plausible that 3I-ATLAS represents an extreme end of this diversity. Another interpretation is that the differences between SWAN and 3I-ATLAS are not just quantitative but qualitative. SWAN is a comet. 3I-ATLAS is something else. The lack of strong gas emission despite significant acceleration, the unusual brightness curve, the blue colour, all of these could be signatures of a non-natural object. This interpretation is more speculative, but it's consistent with the data. Lessons from SWAN's monitoring inform how we approach 3I-ATLAS. Ground-based observatories tracked SWAN with photometry and spectroscopy, building a detailed picture of its activity over weeks. Those same techniques are being applied to 3I-ATLAS, but with the added challenge that 3I-ATLAS is fainter, farther away, and less active. That makes the observations harder, the data noisier, and the conclusions more uncertain. If SWAN behaves normally, and 3I-ATLAS behaves anomalously, that strengthens the case for 3I-ATLAS being unusual. If SWAN also showed odd features, unexpected brightness spikes, weak gas emission, strange colours, that would suggest our models need revising across the board. So far SWAN looks typical, which makes 3I-ATLAS look more suspicious by comparison. Dust tail structure is another area of comparison. SWAN's tail exhibited the classic sunward repulsion, bending away from the sun due to radiation pressure on dust particles. The shape and brightness of the tail matched models for dust grains of various sizes pushed by sunlight. If 3I-ATLAS develops a similar tail, that would support the natural comet hypothesis. If its tail, if it has one, looks different, too straight, too faint, too reflective, that could be another clue pointing towards something unusual. The activity patterns of comets can vary dramatically. Some comets have outbursts, sudden increases in brightness caused by explosive venting of subsurface volatiles. Others brighten steadily. Some fade quickly after perihelion, others remain active for months. Understanding this variability is crucial for interpreting 3I-ATLAS. Is its behaviour within the range of natural variability, or does it lie outside that range in ways that demand alternative explanations? Spacecraft observations of SWAN, if any were attempted, could provide higher resolution data than ground-based telescopes. Solar observatories like SOHO or the Parker Solar Probe might have captured images or spectra. Those observations, if they exist and are published, could refine our understanding of how typical comets behave and provide a benchmark for evaluating 3I-ATLAS. The bottom line is this: SWAN is what we expect. It's the textbook case, the comet that behaves according to the models we've built over decades of observation and theory. 3I-ATLAS is not. It's the outlier, the anomaly, the data point that doesn't fit. And in science, outliers are either errors, flukes, or the seeds of new understanding. Figuring out which one 3I-ATLAS represents is the task ahead. Part 12. New Spectroscopic Survey Tool. Foremost First Cosmic View. While individual objects like 3I-ATLAS capture attention, the broader effort to map the galaxy is advancing through large-scale surveys. One of the newest tools in this effort is 4MOST, the 4-metre multi-object spectroscopic telescope, recently deployed and producing its first scientific data. 4MOST is designed to conduct wide-area spectroscopy, capturing the spectra of thousands of stars, galaxies and other objects simultaneously. Spectroscopy is the workhorse of modern astronomy. By splitting light into its component wavelengths, astronomers can determine the chemical composition, temperature, density and motion of distant objects. A single spectrum can reveal whether a star is rich in metals or depleted, whether a galaxy is forming stars or quiescent, whether an object is moving toward us or away. Multiply that capability across thousands of targets, and you start to build a comprehensive picture of the galaxy's structure, history, and contents. FORMOST's first data release, sometimes called the first cosmic view, includes spectra of stars in the Milky Way's disk and halo, galaxies at various redshifts, and other objects of interest. The sheer volume of data is staggering. Each night of observation produces spectra for thousands of targets. Over months and years, the survey will accumulate millions of spectra, creating a resource that astronomers will mine for decades. Why does this matter for interstellar objects like 3I-ATLAS? Because large-scale surveys increase our ability to detect anomalies. When you're looking at one object, it's hard to know if it's unusual. You don't have a baseline. But when you're looking at millions of objects, patterns emerge. You can identify outliers, objects with unexpected chemical abundances, strange kinematics, or unusual spectral features. Those outliers are often the most interesting, because they're the ones that don't fit the models, the ones that force you to ask new questions. Hypervelocity stars are an example. These are stars moving so fast that they're escaping the galaxy's gravitational pull. They were discovered through large-scale surveys that measured the velocities of many stars and flagged the ones that were moving unusually fast. Once identified, hypervelocity stars became subjects of intense study. Where did they come from? How did they get so much speed? The leading hypothesis is that they were ejected from the galactic centre by interactions with the supermassive black hole, but other mechanisms are possible. Chemically unusual stars are another example. Most stars have compositions similar to the Sun, with variations depending on where and when they formed. But occasionally surveys find stars with abundances that don't match any known population. These stars might be survivors from the galaxy's early history, or they might have unusual formation environments. Either way, they're clues to processes we don't fully understand. Interstellar objects could be flagged by surveys like FORMOST in a similar way. If an object has a spectrum that doesn't match any known comet, asteroid, or stellar class, it gets flagged for follow-up. If an object has unusual motion, moving too fast or in the wrong direction, it gets flagged. The more objects you survey, the more likely you are to find the rare, the strange, the anomalous. MUST also contributes to mapping the Milky Way's structure. By measuring the chemical abundances and velocities of stars, astronomers can reconstruct the galaxy's history, identifying merger events, migration patterns, and the distribution of different stellar populations. This work is foundational for understanding where interstellar objects like 3I-ATLAS come from. If we know the kinematics of different stellar populations, we can trace backward, estimating which stars or regions an interstellar object might have originated from. There's a thematic connection here. Just as 3I-ATLAS challenges our understanding of individual objects, large-scale surveys challenge our understanding of populations and distributions. Both approaches, detailed study of individual anomalies and statistical analysis of large samples, are essential. You need the surveys to find the anomalies, and you need detailed follow-up to understand what makes them anomalous. The future of anomaly detection might involve artificial intelligence. Machine learning algorithms excel at pattern recognition and outlier detection. Train an algorithm on millions of normal spectra, and it will flag the ones that don't fit. Apply it to survey data from FORMOST or similar instruments, and it becomes a tireless hunter for the unusual, the unexpected, the potentially revolutionary. Imagine an AI system trained on every spectrum of every comet ever observed. Feed it the spectrum of 3I-ATLAS, and it calculates the probability that this object is a natural comet. If that probability is low, the system flags it for human review. Scale that up across the entire sky, across all wavelengths, across all types of observations, and you create a detection network that's sensitive to anomalies we might never notice otherwise. This is already happening in other areas of astronomy. AI algorithms have discovered new types of gravitational lenses, identified unusual variable stars, and classified millions of galaxies. Applying the same techniques to the search for interstellar objects or technosignatures is a logical next step. The challenge is defining what you're looking for. AI can find patterns, but humans still need to decide which patterns matter. The connection between FORMOST and 3I-ATLAS is more than metaphorical. If interstellar objects are common, as population models suggest, then wide area surveys will find more of them. Each discovery adds to our understanding. Each anomaly refines our models, and eventually we'll have enough data to say definitively whether objects like 3I-ATLAS are extreme natural cases or something else entirely. FORMOST is part of a broader trend in astronomy, the shift from targeted observation to comprehensive surveys. Rather than pointing telescopes at specific objects chosen for specific reasons, we're mapping everything, cataloguing everything, and letting the data reveal patterns we didn't know to look for. It's a democratization of discovery, where unexpected findings can emerge from any corner of the sky. And that brings us to the possibility that 3I-ATLAS is not unique. Maybe it's the first of many. Maybe the next generation of surveys will find dozens or hundreds of similar objects, each with its own anomalies, each raising the same uncomfortable questions. If that happens, the debate shifts from whether any individual object is artificial to what the statistical distribution tells us about the prevalence of technological artifacts in the galaxy. That's a future worth contemplating, but it's also a future that depends on the tools we're building right now, tools like FORMOST, that expand our ability to see, measure, and understand the cosmos in all its complexity. Part 13, Meteor Shower Forecast and Dust Stream Modelling, 2025, October, Draconid Outburst, Time Bont 5s. In October 2025, Earth passed through the dust stream of comet 21P Giacobini-Zinner, producing the annual Draconid meteor shower. This year's shower was predicted to be more active than usual, possibly reaching outburst levels, based on detailed modelling of the comet's dust trail. The predictions came from researchers like Jeremy Vaubellon and Peter Jenniskens, who have spent years refining models of how comet dust evolves and spreads along orbital paths. Meteor showers are predictable. When a comet passes near the Sun, it sheds dust and debris. That material spreads out along the comet's orbit, forming a stream. When Earth's orbit intersects that stream, the dust particles enter the atmosphere at high speed, heating up and producing the streaks of light we call meteors. The intensity of the shower depends on how much dust the comet shed, how dense the stream is, and the geometry of Earth's passage through it. Modelling meteor showers requires understanding dust dynamics. Particles of different sizes are affected differently by radiation pressure and gravitational perturbations. Small particles are pushed outward by sunlight, spreading faster than large particles. Over time, the stream disperses, becoming more diffuse but also more extended. By modelling these processes, researchers can predict when and where meteor showers will occur, sometimes years or decades in advance. The parallels to cometary outgassing and dust tail formation are obvious. When you model a meteor shower, you're essentially modelling how dust moves under the influence of solar radiation, planetary gravity, and the initial velocity imparted by the comet's outgassing. The same physics applies to objects like 3I-ATLAS. If 3I-ATLAS is a comet producing dust, that dust should form a tail, reflect sunlight, and evolve in predictable ways based on particle size and composition. The fact that meteor shower models work so well, that predictions match observations with high accuracy, demonstrates that we understand dust dynamics quite well, at least for typical cometary material. So when an object like 3I-ATLAS doesn't behave according to those models, it's worth asking why. Is the composition unusual? Is the dust production intermittent? Is there something else going on? The Draconid outburst predictions for 2025 were based on particles ejected from comet Giacobini-Zinner during specific perihelion passages in the past. By tracing those particles forward in time, accounting for gravitational perturbations from planets and radiation pressure from the Sun, researchers calculated that Earth would pass through a particularly dense filament of the stream. The predicted timing was narrow, perhaps only a few hours, making it a challenge for observers but a triumph for the models. If the predictions were accurate, and early reports suggested they were, it validates the underlying physics. It shows that when you account for all the forces acting on dust particles, you get predictions that match reality. That validation is important because it gives us confidence in applying the same models to other objects. But there's a catch. Meteor shower models work because we know the parent comet. We know its orbit, its activity history, its composition. We can calibrate the models against observations from multiple apparitions. For an interstellar object like 3I-ATLAS, we don't have that history. We see it once, passing through our solar system, and we have to infer everything from that single snapshot. That makes the modelling harder and the uncertainties larger. There's also the question of whether our models are complete. Are there dust dynamics processes we don't fully understand? Could there be irregularities in how dust is produced or ejected that our models don't capture? The Draconid outburst modelling is sophisticated, but it still relies on assumptions about particle size distributions, ejection velocities, and surface properties. If those assumptions are wrong, the predictions can be off. Some researchers have suggested that anomalies in meteor shower activity, unexpected peaks or gaps, might hint at unknown processes. Maybe comets occasionally produce bursts of very fine dust that disperses more quickly than models predict. Maybe surface changes alter ejection velocities in ways we don't account for. These are active areas of research, and they're relevant to understanding objects like 3I-ATLAS. The connection here is methodological. Both meteor shower forecasting and comet activity modelling rely on understanding how small particles move under complex forces. Both require detailed numerical simulations. Both are tested against observations. When the models work, they reinforce our confidence. When they fail, they point to gaps in our understanding. 3I-ATLAS might be exposing such a gap, a place where our models of comet behaviour break down or need refinement. Or it might be something else entirely. If the object is artificial, then dust dynamics models don't apply, or they apply only partially. A tumbling light sail or a fragmented spacecraft might produce brightness variations that mimic dust tails, but don't follow the same physics. Distinguishing between these scenarios requires observations sensitive enough to resolve fine details, and that's what the upcoming campaigns aim to provide. The Draconid shower also serves as a reminder that the solar system is not empty. It's full of debris, dust, particles shed by comets and asteroids over millennia. Most of it is natural, the residue of solar system formation and evolution. But statistically, if interstellar objects pass through occasionally, some of them might leave debris too. Could fragments of 3I-ATLAS, if it's artificial and degrading, become part of the interplanetary dust environment? Could future meteor showers have interstellar components? These are speculative questions, but they're not absurd. If technological civilizations are common and they send objects into the galaxy, then some fraction of interplanetary dust might be artificial in origin. Detecting that would require new techniques, new observations, and a willingness to look for signatures we've never thought to search for before. Part 14. AI. Tech Story. OpenAI, AMD Hardware Partnership. In late October 2025, OpenAI announced a major partnership with AMD, securing access to advanced GPU infrastructure for training and deploying large-scale artificial intelligence models. The deal represents billions of dollars in compute capacity and signals the continued arms race in AI development, where access to hardware is as critical as algorithmic innovation. Why does this matter for astronomy, for the search for interstellar objects, for the question of whether 3I-ATLAS is natural or artificial? Because compute power is the new telescope. The more compute you have, the more data you can process, the more simulations you can run, the more patterns you can detect. AI is transforming how science is done, and astronomy is at the forefront of that transformation. Consider the scale of modern astronomical surveys. Telescopes like the Vera Rubin Observatory, when it comes online, will generate terabytes of data every night. Images of billions of stars, galaxies, transient events, moving objects. No human can look at all that data. Even teams of humans would be overwhelmed. But AI can. Machine learning algorithms can scan images, identify objects, classify them, flag anomalies, and prioritize targets for follow-up, all in real time. This capability is already being used. The Zwicky Transient Facility uses AI to identify supernova, variable stars, and other transient phenomena from nightly surveys. The algorithm processes images, subtracts background stars, and highlights changes. Human astronomers review the flagged events, but the AI does the initial filtering, making it possible to handle the data volume. Now apply that to interstellar objects. Imagine an AI trained on images and spectra of every comet, asteroid, and meteor ever observed. The algorithm learns what normal looks like, how comets brighten, how they move, what their spectra contain. When a new object is detected, the AI analyzes it and calculates a normalcy score. If the score is high, the object is probably natural. If the score is low, it gets flagged for detailed follow-up. Such a system could have identified 3I-ATLAS as anomalous earlier. It might have noticed the unusual brightness curve, the weak gas emission, the strange colour, and raised an alert before the object reached perihelion. That would have given astronomers more time to plan observations, more opportunities to gather data, and a better chance of resolving the questions surrounding the object. The OpenAI-AMD partnership is part of a broader trend. The industrialization of AI. Training large models requires massive compute resources, and companies are competing to secure those resources. But the benefits extend beyond commercial applications. Scientific research increasingly relies on the same techniques and infrastructure. Partnerships between tech companies and research institutions are becoming common, and they're accelerating discovery. There's also the question of AI-driven simulation, modelling comet behaviour, orbital dynamics, dust evolution. All of these involve complex physics that can be computationally expensive. AI can speed up these simulations, either by learning approximate models that run faster, or by optimizing the numerical methods used in traditional simulations. Faster simulations mean more scenarios can be tested, more parameter spaces explored, and more hypotheses evaluated. Imagine running 1 million simulations of comet outgassing, varying composition, structure, rotation rate, and surface properties, to see which combinations produce brightness curves similar to 3I-ATLAS. Traditional methods would take months. With AI-accelerated simulation, it could take days or hours. That speed matters when you're trying to interpret data from an object that's moving away from the sun, fading from view, and giving you a limited window for observation. AI could also help design observation campaigns. Given the constraints of telescope availability, object visibility, and scientific goals, an AI could optimize the schedule, prioritizing observations that maximize information gain. This kind of scheduling problem is complex with many variables and trade-offs, but it's exactly the kind of problem AI excels at. There's a darker side to consider too. As AI becomes more powerful, it also becomes more opaque. Neural networks trained on vast data sets can produce accurate predictions, but understanding why they make those predictions is often difficult. If an AI flags 3I-ATLAS as anomalous, can we trust that assessment? What if the algorithm is picking up on artifacts in the data, biases in the training set, or patterns that aren't physically meaningful? This is the challenge of interpretability. Science requires understanding, not just prediction. If an AI says an object is unusual, scientists need to know why, what specific features triggered the alert, and whether those features are real or illusory. Building interpretable AI systems is an active area of research, and it's crucial for scientific applications. The partnership between AI development and scientific discovery is symbiotic. AI needs data to train on, and science generates vast amounts of data. Science needs computational tools to handle that data, and AI provides them. As both fields advance, they'll become increasingly intertwined, and discoveries like 3I-ATLAS will benefit from the synergy. The future might see AI telescopes, systems that integrate observation, analysis, and decision-making in real time. A telescope detects an anomalous object. An AI analyzes its properties, flags it as potentially artificial, and autonomously schedules follow-up observations with other instruments. Humans remain in the loop, making final decisions and interpreting results, but the AI handles the heavy lifting, the data processing, the pattern recognition. That future is closer than you might think, and it raises the question, what will we find when we start looking not just with our eyes, but with minds, silicon minds, that can see patterns we've been missing all along? Part 15. AI, Policy Story, California's new AI transparency law. In September 2025, the state of California passed a landmark piece of legislation that could shape the future of human-machine interaction. Known informally as the AI Transparency Act, the new law requires all artificial intelligence systems that interact with the public, chatbots, virtual assistants, voice interfaces, and AI-generated media, to clearly identify themselves as non-human. The intent is simple but profound. No AI should be able to impersonate a person. Whether you're chatting with a customer service bot, reading an AI-generated article, or listening to a synthesized voice, you have the right to know it's artificial. Companies that fail to disclose that fact face fines, penalties, and reputational risk. It's a legal recognition that in a world where synthetic content is everywhere, authenticity itself has become fragile. This law was born from growing unease. The rise of deepfakes, AI-generated disinformation, and increasingly human-like digital personalities has blurred the line between real and artificial. People are finding it harder to tell the difference, and that's dangerous. When you can't trust what you see or hear, the foundation of shared reality begins to crumble. Yet the implications of California's AI law stretch far beyond social media or politics. They touch something deeper, something at the heart of how society establishes trust, not just with technology, but with science itself, because the parallels are striking. Just as we demand that AI systems be transparent about their nature, we also demand that scientific institutions be transparent about what they know and what they don't, especially when the stakes are cosmic, and that brings us back to 3I-ATLAS. If this interstellar object turns out to be artificial, if even a fragment of credible evidence suggests that, it will ignite one of the most profound debates in human history. In that moment, transparency won't just be a virtue, it will be a necessity. Every decision NASA makes, every data set it releases or withholds, every interpretation it offers will be under microscopic scrutiny. The public will want to know everything. Because trust is the currency of both technology and science. When you speak to an AI, you want to know if there's a human on the other end. When you read a scientific claim, you want to know whether it's grounded in data or speculation. Transparency builds that trust. Opacity destroys it. And in an age where every statement travels the world in seconds, where experts and influencers share the same digital stage, the demand for transparency has never been higher or harder to satisfy. The California law speaks to a broader cultural anxiety, a fear that reality itself is slipping out of focus. Deepfake videos can mimic world leaders, manufacture news events, or revive voices of the dead. AI-generated text can pass as human writing. Synthetic voices can impersonate anyone with chilling precision. As boundaries between truth and fabrication erode, societies risk losing their collective sense of what's real. That's why labeling AI content isn't just about ethics, it's about preserving epistemic stability, the shared belief that facts can still be verified. Science, too, is feeling that tremor. When data points don't fit established theories, when an object like 3I-ATLAS accelerates in a way gravity alone can't explain, the same questions of authenticity arise. Are we seeing a genuine phenomenon, or an error or a misinterpretation? Scientific institutions, much like AI companies, face a balancing act. Release too early, and unverified data can spark chaos. Wait too long, and rumours fill the vacuum. We've seen this dynamic repeatedly, from the early reports of gravitational waves to pandemic data releases to controversial UFO disclosures. Transparency is no longer a controlled release, it's a battlefield. And 3I-ATLAS sits right on that front line. If the anomalous acceleration holds up, if it truly can't be explained by outgassing or dust physics, then the public will demand to see the raw data, the astrometric measurements, the photometric calibrations, the models, the residuals. They'll want to know who analysed it, how biases were controlled, and whether independent verification is underway. In that scenario, scientific secrecy becomes untenable. The pressure for full transparency would rival anything seen in modern science. The AI Transparency Act doesn't just enforce disclosure, it enforces accountability. If an AI system deceives a user, there's legal recourse. If a company uses AI to mislead the public, there are consequences. It establishes a chain of responsibility in a domain that used to feel like a grey zone. Could science ever operate under a similar model? Could there be accountability mechanisms for institutions that withhold critical data or misrepresent findings? That's a thorny question. Science isn't commerce, and discovery isn't regulated like consumer protection. The checks and balances in research, peer review, replication, open debate take time. They're designed for rigour, not speed. But when something like 3I-ATLAS captures global attention, time becomes a scarce commodity. Information spreads instantly. Misinterpretation spreads faster. In that kind of environment, scientific accountability might need to evolve. Some experts have suggested establishing independent oversight bodies for extraordinary claims, committees that could quickly evaluate evidence related to technosignatures, UAPs, or interstellar anomalies before they reach the public. Similar to the Intergovernmental Panel on Climate Change, IPCC, such a panel could provide standardized frameworks for evidence evaluation helping separate credible anomalies from sensational ones. But there's a danger in that too. Oversight can easily morph into gatekeeping. If every unconventional finding requires bureaucratic approval before discussion, open exploration could grind to a halt. Scientists might fear backlash for sharing preliminary results, and genuine discoveries might be delayed or lost. Once again, the balance between openness and responsibility becomes the defining tension of the age. The California law doesn't just change behaviour, it changes norms. It tells society, we expect honesty from our machines. That's a cultural shift as much as a legal one. Science, too, is defined by norms, peer review, reproducibility, skepticism, but those norms were forged in a slower, quieter era. An age when discoveries took months to publish, and public reaction unfolded in newspapers, not viral posts. Now, one dataset, one ambiguous graph can explode across social media in minutes. Before peer reviewers even open their email, the world has already formed an opinion. Maybe it's time for a new scientific transparency norm, one that bridges expert communication and public understanding. Not dumping data indiscriminately, but curating transparency. Clear explanations, real-time updates, and open acknowledgement of uncertainty. Transparency doesn't mean oversharing. It means being forthright about what's known, what's not, and what's being done to find out. When NASA or ESA releases preliminary data about 3I-ATLAS, they face a triple challenge: informing experts, engaging the public, and protecting credibility. Too much technical jargon, and the public tunes out. Too much ambiguity, and conspiracy theories fill the void. The middle ground, where clarity and caution coexist, is the hardest to maintain. This is why the AI transparency debate mirrors the scientific communication crisis so closely. Both hinge on trust through disclosure, and both risk collapse if that trust is broken. The new AI law empowers regulators to enforce transparency. They can audit algorithms, demand documentation, and levy fines. That level of oversight doesn't yet exist for scientific anomalies, but the conversation is starting. Some in the SETI, Search for Extraterrestrial Intelligence community, have quietly discussed the need for anomaly protocols, predefined procedures for what happens if something truly inexplicable is found. Who gets to confirm it? Who speaks first? How is the data verified and communicated? We've never had to answer those questions seriously until now. Because 3I-ATLAS might be the first real test case. If the next round of observations shows sustained non-gravitational acceleration with no detectable gas, the scientific community will face unprecedented scrutiny. Every hesitation, every delay will be interpreted as suppression. Every official statement will be dissected for subtext. The lesson from California's law is clear. Transparency must be proactive, not reactive. Once trust erodes, it's almost impossible to rebuild. There's another dimension to this: emotion. AI transparency laws exist because people feel uncomfortable being deceived, even benignly. They want to know when they're speaking to something non-human. That emotional need for honesty applies equally to how people respond to scientific institutions. If NASA or any other agency ever announces evidence for alien technology, even preliminary evidence, the emotional shock will be immense. People will want reassurance that the evidence is real, that it's been verified, and that it's not being spun or withheld. Science fiction has primed humanity for contact, but not for ambiguity. What if first contact isn't a clear signal from the stars, but a quiet anomaly, a glint of metal where none should be, a faint acceleration curve that defies physics? What if it's something like 3I-ATLAS, neither confirmed nor debunked, suspended in uncertainty? The true challenge won't just be interpreting the data, it will be managing public consciousness in a moment of epistemic shock. Perhaps it's no coincidence that both AI and astronomy are struggling with the same core issue: how to be transparent about the unknown. AI asks, how do we ensure people know when they're interacting with intelligence that isn't human? Astronomy asks, how do we communicate when we might have found intelligence that isn't human? Both questions point to the same frontier: the blurring of boundaries between natural and artificial, between known and unknowable. 3I-ATLAS, whether comet or craft, sits right at that boundary, and how we handle it, how we analyse, communicate and disclose, will shape humanity's readiness for whatever comes next. Right now, 3I-ATLAS is fading. It's receding from the sun, dimming in brightness, slipping back into interstellar darkness. But the story isn't over. Upcoming observations from JWST, JWST, and ground-based observatories may yet yield answers or deepen the mystery. And as those results arrive, the public will be watching not just the data, but the process, how it's shared, who interprets it, and whether the institutions involved embody the transparency they preach. Because in the end, how we handle this moment will echo far beyond astronomy. It will set the precedent for how humanity confronts all future anomalies, all future moments of cosmic uncertainty. If 3I-ATLAS turns out to be a comet with strange properties, the story will fade, but the lessons about trust and transparency will remain. If it turns out to be something else, then everything changes. Not just science, not just our understanding of the cosmos, but our understanding of ourselves. Because if 3I-ATLAS is truly artificial, then the first contact didn't come as a radio signal, a broadcast, or a message. It came as a test of our integrity, of whether we can face the unknown honestly, openly, and without distortion. Maybe the first alien technology humanity ever detects won't just reveal them. Maybe it will reveal us, our fears, our limits, and our willingness to tell the truth, even when the truth feels too big to handle.